This is the ELEC 1510 Logic Design Lecture 4, Video 2, Boolean Algebra Theorems Part 2, corresponding to textbook section 2.4. Alright, so we're going to go into some more complicated theorems this time that use the basic theorems that we talked about in Lecture 4, Video 1. So if you haven't watched that, please go back and watch that because I'm going to use those theorems. Okay, so the first theorem is the distributive theorem, which has two little parts to it. The first part is where x and or multiplied. So whenever you have this multiply with two variables just next to each other, that's an and function. So x multiplied by y plus z, in this case y or z, is equal to x times y plus x times z. So you just distribute the outside variable to the two inside variables just like you do in normal algebra, and this essentially comes out to be x and y or x and z. Alright, so that one's pretty self-explanatory. The second one here is a little bit more complicated. X or y and z, or potentially the way that you can just say it more simply, x plus yz is equal to this first term, x plus y in parentheses, times x plus z in parentheses. All right, so this is a little bit more complicated, so I'm going to demonstrate how this works on the next slide. If I distribute this parentheses out into the second parentheses using FOIL, so first outside, inside, last, the first two terms are x times x, so that's this term times this term. Now outside is x times z, so plus x times z. Then the inside terms, plus x times y. Then the last terms, plus y times z. Okay, so we know from the lecture 4 video 1 that x times x is just equal to x. So x plus xz plus xy plus yz is a simplification of this first term. Okay, so then I can factor out an x from these two terms to get x times 1 plus z plus xy plus yz. Now 1 plus z, 1 plus any variable, is just equal to 1. So this comes out to be x or xy or yz. And now I can pull the exact same trick on this variable, or that term, and the second term, xy. I can factor out an x, and then I get 1 plus y, and then the 1 plus y just becomes a 1. And so in total, this will become x plus yz. Okay, so De Morgan's theorem is one of the most commonly used theorems that we're going to use in algebraic simplification of Boolean functions. This is kind of a complicated one, and it has two main forms. The first form here is that x or y in parentheses prime is equal to x prime y prime. So the way that I like to think about this is that there's an operation here which is or, which can also be called plus, and the operation changes. So it was an or, it becomes an and. You flip the operation, and then you get rid of the outside prime, but you make the two inside variables prime. Now, you could also have written this as x prime or y prime prime is equal to xy. Because if these variables had been primed, then the double prime of these goes back to being xy. So both of those are equally valid. And let's prove that using a truth table. So x and y can take the following states. They can both be 0, x can be a 0 and y can be a 1, x can be a 1 and y can be a 0, or they can both be a 1. Now I've written out both their corresponding complements as well. So x or y, this term, which we'll need up in here, is going to be a 1 if either one or both of the input variables, x or y, is a 1. So that's going to be 0, 1, 1, 1. X or y prime is going to be the opposite of this column, so that's 1, 0, 0, 0. Now x prime, y prime, here, we're going to look at these two columns, and this output will be a 1 only when both of this and this are a 1. So it's a 1 here and nowhere else. And so now we've proven, using a truth table, that x or y in parentheses prime is equal to x prime, y prime. So that's the first case of De Morgan's theorem. The second case of De Morgan's theorem is where we flip the operation. So now we have x and y in parentheses prime is equal to the opposite operation in OR, and then we flip the variables in terms of their complements. So x and y in parentheses prime is equal to x prime plus y prime. Now this could also be written as, just as I did in the last version, x prime y prime parentheses prime is equal to x or y. All right, so let's prove this again using a truth table. I have all of the states of x and y written here, all of the corresponding states of x prime and y prime. So now let's look at xy, which comes into the equation here, which is only going to be a 1 if both x and y are 1. So that's a 1 only on the bottom row. Now xy prime is just the complement of xy, so that's 1, 1, 1, 0. So now looking at x prime or y prime in parentheses, that's going to be a 1 if either one of these two columns is a 1. So we have a 1 here, a 1 here, a 1 here, and a 0. So now we've shown that for these two variables, xy parentheses prime is equal to x prime plus y prime. The absorption theorem in the first case says that x plus xy is equal to x. Now I've already kind of proven that this is true in a previous example, but let me just quickly show again how this works. If I factor out an x from this expression, I'll get x times 1 plus y, and then 1 plus any variable is always just equal to 1. So that will be equal to x, which was what the original expression was equal to. The second case of the absorption theorem says that x times parentheses x plus y is equal to x. If I distribute out the left side of the expression, I will get x times x plus x times y. Now x times x is just equal to x plus xy. Again, I can factor out an x to get 1 plus y, which is equal to 1. And so that comes out to be x.